Hello everyone and welcome to KognitoKey. Imagine for a second that you're standing right in front of a massive industrial furnace. Maybe you're on the floor of a busy steel forging plant or looking closely at this giant vat of glowing molten glass. The heat radiating off the surface is absolutely intense, right? It's glowing this incredibly bright orange and white. It is a harsh, really extreme environment. Now, think about how we usually measure temperature in our everyday lives. We just use the thermometer. But if you were to actually stick a standard contact-type thermometer into that molten metal, no way, it would be instantly destroyed. It would literally just melt away in a matter of seconds.
So, that brings us to a really fascinating question. How do you actually measure a raging furnace without completely melting your thermometer? We know for sure that traditional contact-type instruments are practically impossible to use on these highly heated bodies without getting completely destroyed. We need a way to figure out exactly how hot something is, but from a safe distance, without ever actually touching the object itself. And that is exactly the fascinating engineering puzzle we are going to solve in today's explainer.
Well, the solution is an incredibly ingenious instrument known as the Optical Pyrometer. This right here is our non-contact hero device. By definition, an optical pyrometer is a temperature measuring device that brilliantly solves our whole extreme heat problem by using light instead of physical touch. The fundamental principle here is actually quite simple, but honestly, it's absolutely genius. It works by matching the brightness of the extremely hot object you are looking at directly to the brightness of a small internal filament placed right inside the pyrometer itself.
Let's actually take this instrument apart and see what's going on inside. The construction of the optical pyrometer is surprisingly simple and really elegant. It's basically just a cylindrical tube. So let's do a quick teardown, starting from the front end and moving straight to the back. First, at step 1, right on the front end, we have a lens. Moving inside the cylinder, at step 2, there is an electric filament lamp kept directly in the line of sight. At step 3, right before the viewing end, we have a special optical filter. And finally, step 4 is the eyepiece on the other end, which is where the operator actually looks through the device.
Now, that little electric lamp inside, it doesn't just glow all by itself, of course. It is powered by what we call the control circuit. This lamp is connected to a battery to provide power, an ammeter to measure the electrical current, and a rheostat. And you know, the rheostat is absolutely crucial here because it acts like an adjustable dial. It allows us to carefully adjust the exact amount of current passing through the filament, and changing that current directly changes how brightly that filament glows. So what happens when you actually point this cylindrical pyrometer at your heated object? Well, that front lens does a very specific, important job. It takes the radiated energy, all that bright light and heat glowing off the furnace or the molten metal, and it focuses it. It targets that glowing energy directly onto the electric filament lamp sitting inside the cylinder. So when you look through the eyepiece, you're essentially seeing the glowing hot object in the background with the small filament superimposed right on top of it. Interpreting what you're seeing comes down to what I love to call the Goldilocks working principle. You look through the eyepiece and you adjust the rheostat to change the filament's current. If the filament looks distinctly bright against the background, well, its temperature is hotter than the source. If it looks dark, the filament is cooler than the source. But here is where the magic happens. When you adjust the current so perfectly that the outline of the filament completely disappears and blends flawlessly into the background, the temperatures are exactly equal. You have found the exact temperature of your highly heated object. Now you might be wondering, hey, what about that filter mentioned earlier in the teardown? Its specific role is creating monochromatic light. You see, when you're looking at incredibly bright, glowing objects, dealing with all the different wavelengths of visible light can make matching the brightness quite tricky and honestly pretty uncomfortable for the human eye. The filter, which is placed right in front of the eyepiece, isolates a single wavelength. This creates clear monochromatic light, making the visual matching process highly precise, very safe, and just super easy to see. It's really easy to see why industries absolutely love this tool. The advantages of the optical pyrometer are incredibly strong. First and foremost, it offers extremely high accuracy. Once that filament perfectly disappears, you know for a fact you've hit the target temperature precisely. And secondly, it's a 100% non-contact measurement. Because you never have to physically touch the heated body, the instrument doesn't melt, it doesn't degrade over time from extreme heat exposure, and you can safely use it for just a massive number of intense industrial applications. But to give you the complete picture, we definitely need to weigh the facts by looking at the limitations. There are a few disadvantages you have to consider. First, the object must be hotter than 700 degrees Celsius. Why? Because the entire working of the pyrometer depends on visible light being emitted by the heated body. If it's not glowing, this simply doesn't work. Second, the accuracy relies entirely on a human's eyes to adjust the filament current until it vanishes, so naturally there can be slight human error. And finally, it is entirely useless for measuring the temperature of clean gases. Clean gases just do not radiate visible light in the same way that solid objects or liquids do.
And this brings us to a really fascinating boundary in our understanding. If optical pyrometers absolutely need visible light to work, how do we measure the invisible? How in the world do we measure the extreme heat of those clean gases? I want to leave you with that provocative thought about the true limits of human measurement and engineering. Thank you so much for joining me today. If you found this explainer helpful and want to keep unlocking new knowledge, please subscribe to the KognitoKey channel, give this explainer a like, and share it with your friends. Keep learning, and I will see you next time.